Hello everyone, this is GATE 2023 Life Sciences Section P Biochemistry. Question number 46. If the extracellular concentration of sodium ion is 10 times more than its intracellular concentration, then the sodium equilibrium potential at 20 degrees Celsius in millivolt is dash. Assume that the membrane is permeable only to sodium ions. Use R is the gas constant, as 1.987 calorie degree inverse mole inverse, and F is a Faraday's constant, which is equal to 23062 calorie mole inverse volt inverse. Okay, so here we have to use Nernst equation. Okay, we have to use Nernst equation, and Nernst equation is very nicely explained in this NPTEL online course reference. I'll explain to you. This is a semi-permeable or permeable membrane which only allows transfer of Na plus ions. Okay, which allows transfer of Na plus ions. So let's consider that this is the intracellular concentration of sodium, and this is extracellular. This is extracellular concentration of sodium ions. So in the question they have said that the sodium ion is 10 times more than its extracellular concentration of sodium ion is 10 times more. So that means the extracellular concentration is 10 times more than the intracellular concentration, right? This is what it means. This is 10 times more. So we have 10 times more Na plus ions, right? 10 times more Na plus ions which are in the extracellular concentration. Okay, so now as we know, we have a higher concentration of Na plus in the extracellular region. This is the extracellular region, whereas there are very low Na plus ions in the intracellular concentration. Okay, so be a concentration gradient, right? So extracellular concentration is higher than that of intracellular, and and it is intuitive that the Na plus will move from higher to lower, right? It will move from higher to lower. So while moving from higher to lower, it develops a concentration gradient, and since Na plus is it is a positively charged ion, it will also create a potential gradient. Okay, so this is a solution, so it will also have some negatively charged ions here. It might be Cl minus, it can be OH minus, that could be negatively charged ions also. So when this Na plus is moving, it creates a charge. It creates a potential gradient on this membrane. So this potential gradient is dependent on the concentration. So whenever there is a concentration difference, there will be movement of ions from higher to lower concentration, right? From higher to lower concentration, and whenever there is this movement, we'll get a potential gradient. Okay, this potential gradient is also referred to as E. Okay, and this potential gradient is because of sodium ions, hence we'll refer to as E, and we'll have a subscript Na because this is because of sodium ions. Okay, and this potential gradient is also known as equilibrium potential. Okay, this is the equilibrium potential of sodium. This is equilibrium potential. This is equilibrium potential of sodium ions. Okay, we need to find this equilibrium potential, and for this we'll use Nernst equation. Okay, this is clear. We have higher concentration of Na plus ions in the extracellular solution as compared to that of intracellular. So there will be movement of ions from higher to lower concentration gradient, and because of this concentration gradient there will be a potential gradient. Right, there will be a potential gradient, and this potential gradient will lead to the formation of a equilibrium potential which will be maintained, which will be caused depending upon these two concentration gradient, and we need to calculate these equilibrium potential. So let's understand what is a Nernst equation. So Nernst equation is given by equilibrium potential of the given ion. In our case we have a sodium ion, is equal to RT, where R is the real gas constant, T is the temperature, absolute temperature in Kelvin, Z is the valency of sodium plus ion, okay, and F is the Faraday's constant into natural log of Na plus concentration extracellular upon Na plus concentration intracellular. Okay, so we need to find the equilibrium potential of Na plus, so we just need to plug in the values. We also know from the question we know the gas, they have given a gas constant to be 1.987 calorie degree inverse and mole inverse. The absolute temperature here they have given is 20 degrees Celsius, but we need it to be in Kelvin, so 20 plus 273.15, which is equal to 293.15 Kelvin, right? Z is the valency of sodium. So sodium has total 11 electrons. These 11 electrons are occupied as 2, 10 and 1. This one electron is donated by the sodium to become Na plus, right? So it has valency plus 1, right? And the Faraday's constant, they have given the value to be 23062 calorie mole inverse V inverse. Okay, we already know that 10 times sodium ion is present in the extracellular concentration is 10 times that of the intracellular Na plus concentration, right? So let's plug in the values. We'll have gas constant 1.987 into T, which is 293.15 upon valency is plus 1 into Faraday's constant 23062, right, into natural log of, so extracellular we have 10 times that of intracellular, so it will be like this. Okay, So let's solve. This is equal to 584 approximately upon 23062 into natural log of 10. We all know what is natural log of 10. So this division is 0.0253 into 2.303 0584 volts. Okay, so equilibrium potential is in volts, and in the question they have asked to convert to millivolts. To convert into millivolts, we need to multiply by 10 to power 3, right? Milli is 10 to power 3, so it will become 0. So this will become how much? 58.4 millivolts. So the equilibrium potential of Na plus is 58.4 millivolts. Okay, thank you.